Okay, so I guess I should get started. This is the second lecture. Yesterday we started this lecture series by talking about complex manifolds and holomorphic vector bundles, kind of general nonsense. And most of that, hopefully, you've seen some version of before. If not, well, maybe you have to dig into the notes to continue following. But maybe one of the examples I talked about was I constructed this J, which was also given in one of the problems to show that it's well defined. And then we looked at the eigenspaces. So since the eigenvalues are plus or minus square root of -1, in order to diagonalize it, you have to work over the complex numbers. And then you, because this J is a real operator, the eigenvalues come in pairs. So every eigenvector, the complex conjugate, will be another eigenvector. And so the plus eigenvectors, plus square root of -1, we called T1, 0. And then the other ones were T0, 1. Then, of course, you can look at the cotangent bundle, the dual, and look at complex valued things. So this also has a splitting. This J induces a J on here. And so T1, 0 star x plus T0, 1 star x. These are actually dual bundles. I think I mentioned this is a holomorphic thing. This one is not holomorphic. But now we want to look at, so the sections of these things are complex valued differential forms of degree 1. And so they get a splitting into differential forms of by degree 1, 0 and of by degree 0, 1. And now we want to extend this splitting to all of the possible differential forms. So we're not going to work with real differential forms. It makes more sense in the complex setting to work with complex differential forms. So we look at the skew-symmetric degree R tensors, so lambda R of T star X tensor C. These would be differential forms of degree R with complex coefficients. But this is a product and this is a sum, so when you distribute this, you will get the sum over all P plus Q equal to R, and then you'll have P of these guys and Q of the others. Sorry? No, it's a wedge. Thank you. So this is an object that comes up a lot. So we'll just give it a short form of notation, lambda PQX. So the sections of this bundle, so another vector bundle over X, and the so the sections are called PQ forms. So, and last time we talked about how if you've got a local coordinate system, in local coordinates, so dz1 up to dzn, this will span or give a frame for T1, 0 star X, and the complex conjugates these will span the complex conjugate space, which is T0, 1. And so the elements here will a frame for this bundle would be dzi1 wedge dzip wedge dz bar j1 dz bar jq, and we have a short form for this as well. So this will be dzi. This I is the multi-index with p entries. And this one, dz bar j. J is a multi-index with q entries. So that's the definition. And so a typical differential form, say alpha, as a PQ form, will look like fi j bar dzi wedge dz bar j. And this brings me to one of the things that shortens my writing a lot. I like to use this summation convention. So when you see a repeated index with the same conjugation parity, you sum over all possible values of that index. This actually can get a little confusing when you're not used to it, but it embodies all the duality that you find in all these forms. So if you use this notation enough, it's actually more than just shortening how much you write. It sort of clarifies the meaning of many things. And another aspect is which indices are lower and which indices are higher. So for the frames for differential forms, the indices are raised indices. Their coefficients would be lowered indices. And so you can identify how objects transform covariantly, contravariantly, and so on when you get used to this. But I'm not going to write down formal rules that explain all that. It's just a matter of practice. So, okay. So we have differential operators on differential forms. So the important operator, exterior operators. So for this space lambda r x, which is that, so maybe tensor with C, you have the exterior operator D, which you all know. So this is actually, you think of an object here as a tensor, and then you take the derivative of that tensor, which means the derivatives of all the coefficients, but then you have to take the skew-symmetric part. So I emphasize that for later reference. So for differential forms, you also have, so for PQ forms, maybe for lambda PQ, you also have two operators, D and D bar. And what are their definitions? So D of alpha is D F I J bar, DZ bar, or DZK, DZK wedge, DZI wedge, DZ bar J. And then D bar of alpha is similar. So this brings me to another point of the notation. So in this expression here, there's not a unique collection of coefficients Fij expressing alpha, if you write things in this way. And the reason is that these objects are gotten from the tensor product by taking a quotient. You apply skew symmetrization, you say, and you annihilate all the things that are not that are symmetric in some sense, or not fully skew symmetric. So that means that you are allowed to reorder these things, and they just might change a sign. If you want to get uniqueness, there are two standard ways. One is to make these indices increasing. That way is not a good way for most of the geometric calculations, and the reason is that it completely forgets the skew symmetry. A better thing is to assume that the coefficients are also skew symmetric. And if you assume that, then again you have a unique expression. But then when you write down these operators, these coefficients are not skew symmetric written in this way. So later on when we work out this Bachner-Kodaira identity, the formulas for these things will look a little bit different than they do now. But for the purpose of computation, you can write this down, and then if you wish, you can skew symmetrize the coefficients appropriately. Okay, And let me now write down, without proof, a proposition. So the proposition is that this operator D is equal to D plus D bar. Oh, by the way, so I defined this D for PQ forms, but it's true for any PQ forms. It's not fixing the P and Q in any way. Okay? And so the claim is that this D is round D plus D bar for differential forms. Now, this is something that involves computing the chain rule in a holomorphic coordinate system, but you can also look at this D and D bar operators in a slightly different way. You can check that, let me make a remark. So check that this D acting on PQ forms is equal to, you take the exterior operator to the PQ form, and then you apply the projection to P plus 1 Q forms. So the projection, meaning the projection from this direct sum here. Okay? And D bar, similarly, on lambda PQ is P pi PQ plus 1 following D, the exterior derivative. And so the claim I'm making is that when you compute this exterior derivative on this very, very long thing, the formulas simplify greatly. And that's not at all obvious. And you may think, well, maybe it just comes from the nature of the splitting, but it definitely does not. So if you had any j that satisfies j squared as I define everything I've done up to here, as long as you define D and D bar in this way, but this relation would not hold in that generality. Okay? So this is special to complex manifolds. In fact, it characterizes when a manifold is complex. That's a theorem called the Newlander-Nirenberg theorem, which I won't get into here. Okay. So these are some of the differential forms that we'll deal with, but we will need to deal with more than these. So let me talk about twisted differential forms. So the word twisted is often used in this subject by complex geometers. It basically means that the differential forms take values, instead of taking values in the complex numbers, they take values in a more general holomorphic vector bundle. Or maybe a complex vector bundle. If you ultimately we'll be working just with holomorphic vector bundles. So these are sections of lambda r x tensor with E, where E to X is a vector bundle. So usually a holomorphic vector bundle. And the word twisted comes from the fact that these vector bundles have curvature, which we're going to discuss later on, and the curvature plays a major role in whether or not you can solve the Cauchy-Riemann equations. So, okay, so well, you can also have this splitting here. So you can have lambda PQX tensor E. So locally, so if you have a section sigma of a twisted differential PQ form, it will look typically like F I J bar alpha DZI wedge dz bar j tensor with E alpha, where E1 through ER would be a frame for E. Now, these operators, they typically do not have an exterior derivative without some additional assumptions. And we're going to talk about those in just a moment. So typically, to obtain a twisted exterior derivative, requires more data. So, I mean, well, you could just imagine maybe just applying, say, this round D operator to these functions. So, for example, you could just apply this D to these F alpha ij bar, and then it looks like you have a P+1 Q form with values in the vector bundle, except when you change coordinates and you change the frame of the vector bundle, you'll see that you no longer have a section of the vector bundle. So something gets messed up. So this is analogous to the following phenomenon. Imagine a surface embedded in R3. And now imagine having a vector field which is defined on R3 but is tangent to the surface. So this is a vector-valued function because you're in R3. So you can certainly take the gradients of the components, the derivatives of the components of this. And so you now again have a vector field in R3, but what you'll see is that it's no longer tangent to the surface. And so that's exactly what happens here as well. You're no longer a section of this vector bundle. But remarkably, the error only occurs in zeroth order terms. So as long as you remove some zeroth order part, you can again make it a twisted differential form. But there are unfortunately many, many ways to do that. So I'll discuss those in just a minute. But I just want to end the discussion of differential forms with one remark here. I said typically, but there is actually one operator which is well defined and it's fundamental for us. So, exceptionally, one of the exterior operators is well defined. So that's the D bar operator. So in fact, I claim that, so D, I'm going to define D bar of sigma is going to be by definition, so D bar of F alpha I J bar EZ I wedge DZ bar J tensor E alpha. So I can think of this locally. This is just some differential form, which I'll write as F alpha. It's a PQ form for each element of the frame. And so this is, I'm giving you now the definition of this thing. You take this differential form that's appearing in this particular basis given by this frame, and you apply D bar to it. And I claim that that's independent of the frame. So this operator is well defined. Okay, so suppose on the other hand that we write sigma as F alpha tilde tensor E alpha tilde, where E alpha is another frame, and these are the coefficients of this same sigma with respect to this other frame. So, well, E alpha tilde is going to be some matrix of holomorphic functions times E alpha. So it'll be, well, this is maybe G alpha beta times E beta. There's a summation over the beta here, okay? And so therefore, F tilde alpha, E tensor E tilde alpha is F tilde alpha G alpha beta tensor E beta. So this is the transpose operation on the coefficients. Okay? So this is the expression for F beta. This is the transformation law that these things satisfy. So now if I compute this d bar of F tilde alpha tensor E tilde sub alpha, right? This F tilde alpha, let me write it this way. So this is equal to d bar of F tilde alpha tensor G alpha beta E beta. These are just matrix multiplications. So these are functions. So they're treated as numbers point-wise multiplying these vectors. But they're also holomorphic. So they can go inside d bar because d bar just sees them as constant. D bar of F tilde alpha G beta alpha tensor E beta. But this is exactly d bar of F beta tensor E beta. So you see that the expression is exactly the same no matter what holomorphic frame you're using for the vector bundle. I should say that, emphasize that, if E is holomorphic vector bundle. Any questions? Okay, so you see where the round D operator, this would fail because exactly at this step, you would not be able to move the G alpha beta inside round D. But you would if you subtracted something that dealt with just the derivatives of these G alpha beta. There are many ways to do that, is what I'm saying. Oh, maybe one last remark. You keep saying that, but this time, this will be a last remark before I move on past differential forms momentarily, which is a convenient. But one of the benefits of this geometry is that you can sort of reduce the equations that you're dealing with to one special case. So you'll see that in action later, but I want to rewrite this twisted PQ forms. This E is a holomorphic vector bundle now. Okay? These twisted PQ forms I want to rewrite in this way, but in such a way that this P is always N. So I claim, well, let me just write it out. So this is equal to lambda P of T10x, right? Wedge. So wedge is just a tensor product with the skew symmetry. So for this purpose, let me write it as tensor product. So I have lambda 0 q of x tensor E. But you see this T10 is a holomorphic vector bundle, and so taking p-th wedge products makes this a holomorphic vector bundle. And then you can tensor it with this E. So maybe after isomorphism, you can write this as lambda 0 q of x tensor E prime. So E prime is a tensor product of this and this. So you can reduce to the case n equal, or p equals 0. Also, I actually want to do the case p equals n as well. So then I just write this as lambda n of T10x tensor with its dual. This should be stars. T10 x dual. And then I've got my lambda 0 q and E prime. And now I take this and move it to here. So if you remember, this is the canonical bundle. This is the canonical bundle. So this is the dual of the canonical bundle. That's the inverse. And so if you tensor with the dual of the canonical bundle, you get, so this will be lambda n q x tensor E double prime. So you can always express PQ forms in a holomorphic vector bundle, as 0Q forms with values in another holomorphic vector bundle, or as NQ forms with values in a third holomorphic vector bundle. There are advantages to doing all of these things, but this one yields the simplest a priori estimates in appearance. So that's why I'm going to use that later on. Okay, good. So far, so good. So that's a rapid, I should leave this here. It's a rapid discussion of differential forms, possibly with values in a possibly holomorphic vector bundle. So what we want to do typically with differential forms is, of course, integrate them. That's their primary introduction was as objects you integrate, although there's many more uses. But so we're eventually going to want to make Hilbert spaces, L2 kinds of spaces. So what we would like to do is measure the norms of differential forms, or possibly twisted differential forms. And the objects that measure these norms are objects that are inner products on the pointwise vector spaces, the fibers of the vector bundle particular vector bundle that we're looking at. So those are called Hermitian metrics. Unfortunately, this term Hermitian metrics gets used in two different ways in the mathematical universe, or at least the one that I occupy. One of them is as metrics for the fibers, inner products for the fibers of vector bundles, but another one is for a Riemannian metric on a manifold, which is something called Hermitian, which I'll explain. So I'll explain both of those, and we will use both of those. And there's a reason that the same name gets used. There's actually a way to pass from the manifold metrics to see them as a special case of these more general vector bundle metrics. Okay, so let's start with the quick one. So vector bundle version. I'm not going to say a lot about this. So this is Hermitian metric is I'll put smooth, but later on we'll talk about versions of these that are not quite smooth, but still have nice properties. Family of inner products Hermitian metric for a vector bundle E is a smooth family of inner products for the fibers of E. And you may want to know, what do I mean by smooth? So, and one way to do it is you choose a frame for this vector bundle. So smoothness is a local property. So to check it locally somewhere, you choose a frame and you look at the corresponding matrix given for this inner product by that particular basis. And that matrix will depend on the base point. And so it'll be a function into the Hermitian matrices from the base manifold locally. And if that function is smooth, then you say that the metric is smooth. If that function is measurable, then you say that the metric is measurable. But the caveat is that you have to use the most regular possible frame to begin with. It can never be any smoother than the frame. There's another sort of quick way to say exactly the same thing. So if you think about it, a Hermitian metric, okay, so let's write such a thing. You stick in two vectors, maybe v and w, but if you multiply v by lambda, a scalar, I like the word scalar, then the lambda can come out here, but then it can go back in as a conjugate. So you really can think of this H not as acting on a pair of vectors, but rather on a tensor product, V tensor W, which has exactly this particular relationship with scaling. You can scale either of the vectors. So it means that it takes an element of E tensor with the vector bundle, which is the complex conjugate of E, and produces a complex number. So it produces something in C. So it's actually an element of the dual of this thing. So it's really a section of E star tensor E bar star. The bar and the star can commute. So, so this H is a section of this thing. And now you can talk about the regularity of this section. And the definition of that is exactly what I said before in terms of the frames. So, this is really the definition of a Hermitian metric. And it can be smooth or measurable. If it's measurable, it's not defined point-wise and so on. So you have to be careful if you're going to work with just measurable metrics. Later on, we will discuss certain kinds of very singular metrics, but they won't be as bad as measurable. Okay, so far so good. Okay, what about Riemannian Hermitian metrics? So let's say X is a complex manifold. Complex manifold. So definition: a Riemannian metric G on X is Hermitian if, when you take this operator J that we introduced before and you pull back this G, it doesn't change. What that means is G of JV, JW is G of V and W. So that's what Hermitian means. Okay. Okay, so now you can, this is a Riemannian metric is a Euclidean, not a Hermitian. It doesn't have Hermitian symmetry for the tangent bundle of a manifold. But you can also complexify this tangent bundle. And then you complexify the metric, which just means instead of it being real linear, it's now complex linear, but not Hermitian. So if you scale by a complex number here, it doesn't come out as a complex conjugate. It comes out as the same number. Okay? So that's called the complexification. And so if you've got one of these Hermitian metrics, you can extend it, and it's no longer going to be positive definite because it's over the complex numbers, but it's still going to be a bilinear, symmetric, non-degenerate form. But then you can look at what happens to it in terms of this splitting that we've been discussing. So in terms of the splitting, this metric will be given by 4 quantities. And I'm not going to work out what these quantities are. I'm just going to tell you the answer. And then you can do this either following the notes or try to do it on your own. It's not so difficult. But remember, these are the eigenspaces for the eigenvalue square root of -1. And this is its complex conjugate. So it turns out that if it's Hermitian, if the Riemannian metric is Hermitian, then this A and D are both 0, and B is the complex conjugate of C, or B. Okay. And then this B will be, I guess maybe I want to write it this way. And then this B will be a Hermitian metric for the vector bundle T10 of X. So that's the relationship between the two. In terms of coordinates, if you've got coordinates, you can write your metric G well, I don't want to deduce this, so I'm just going to tell you what the outcome is. This matrix B will be something like Bij bar, dzi, and then symmetric product, dz bar j. So that would be the expression for a Hermitian metric. And this, with respect to this, with the complex coordinates and this splitting. Okay? You're not obliged to write it in these terms, but this is particularly compatible with the complex geometry. Okay, another important quantity that Hermitian metrics have is that they are related to a differential 2 form, so it's called the metric form, and it's defined, call it omega sub g. So omega sub g on vectors v and w will be g of jv w. Okay? So this is skew symmetric because this is equal to g of wjv by symmetry because it's a Riemannian metric. But then this is invariant under j. So you can put a j here and a j here, and you haven't changed the quantity. But j squared is minus the identity. So this is minus g of jwv, which is minus omega g of wv. So that shows you that it's actually a differential form of degree 2. The differential form omega g from this is equal to bij bar dzi wedge dz bar j. Okay? So you can either define it invariantly like this or define it in terms of coordinates. It's the same. So far we've got some of the ingredients that we need to define L2 spaces, namely we can measure the norms of our sections. But then we have to integrate them, and there are a couple of ways to do that, but for now I'm just going to focus on one of them. So to integrate them, I also need a measure. So, well, if I'm on a Hermitian manifold, I have a Riemannian metric, so I can certainly take the Riemannian volume form. So this is just going to be the locally the square root of determinant of gij, and then dx1 dx2n. These x's are not the real or imaginary parts, they're just any real coordinates. And gij is the metric expressed in terms of those coordinates. But you see, when you look at the structure of this metric, you see that somehow, I mean, there's this sort of a funny sign business, but that has to do with how you ordered the 1, 0 and the 0, 1 vectors. But somehow it looks like the determinant of this thing up to a sign is the absolute value squared of something. So, and it's a nice Hermitian metric. So when you take this square root, good things should happen. And in fact, that does happen. This is actually equal to omega g to the n over n factorial. This is the nth wedge product of this form. So you always get a volume form for a complex manifold just by having the metric form. You don't have to take any square roots. And that greatly simplifies many things. It also has an interesting advantage that if you have a submanifold, you can restrict your metric to that submanifold, and that's just pulling back this form by the inclusion of the submanifold. So the area form on that submanifold will be just the top exterior power of this omega g restricted to that submanifold. So you get a very uniform way of writing down measures for these things. That will be useful at the end when we talk about the L2 extension theorem. Okay, so let me get back to this business here. So here we had a well-defined operator, d bar, but I mentioned that you cannot extend the standard exterior operators to twisted forms, or sections of vector bundles even, without doing something to them. And so that's the theory of connections. And I want to start discussing that today. So connections are these very, very general things. They work in the extreme generality in differential geometry, but for vector bundles, they have kind of a simple incarnation. So so let's just give the definition. So we want, so X is, well, let's say M is going to be a smooth manifold. And then E will be a complex vector bundle. There's no sense in which it can be holomorphic at this stage. So a connection, D, is a linear map. Say it like this. A linear map D from the sections of E. So it takes in a section and spits out differential one form with values in E, so a twisted form. It's linear over the complex numbers, but this object here has a different module structure as well. It's complex vector bundle. You just change the word holomorphic to the word smooth in the definition of holomorphic vector bundle. Okay? I wrote it in the notes, but maybe I didn't mention it in the lecture. Thanks. In most of our applications, the vector bundles will ultimately be holomorphic. So if you prefer, you can just think of this as a holomorphic vector bundle for now. Okay? This thing is not a holomorphic vector bundle, though. So, right. So it's a linear map such that we need one additional piece of information. So as I was starting to say, this object here is also a C infinity of M module. So you can multiply a section by a smooth function, and you still have a section. And this map linear not with respect to that structure. Okay? It's linear with respect to the multiplication by scalars, but not multiplication by smooth functions. So we have to say what it does to smooth functions. And if we take our Q from the differentiation, so we want it to satisfy a Leibniz rule. So this is the rule. So D of, if you have a function f and a section sigma, then this will be df tensor sigma plus f d sigma. Okay, so that's the definition of a connection. So this is the part that differentiates the coefficient. And if we were lucky, if this vector bundle were trivial, for instance, this would already be a well-defined section of this. But in general, this won't be a section of this bundle. And so, because these functions, well, anyway, that's not the right way to say it. So just forget what I was just saying. This is the correcting term, if you like, in some sense. Okay, so notice that this term here does not depend on the connection D. Okay. So note, so if you have two connections, D1 and D2 are connections, then so D1 minus D2, let's call this thing A, satisfies A of F sigma is F of A sigma. This is not differentiating. Okay? So, and in fact, conversely, if you've got, so this A here, A is an endomorphism of E but with differential form coefficients. In other words, it's a section, i.e. a section in gamma of m. So this will be T star m tensor the endomorphism bundle of E. And this endomorphism is just E tensor E star, linear maps from E to E. Okay? All right, conversely, if you've got a connection, you can add to it such an endomorphism, and you'll get a new connection. So you can check that this Leibniz rule would be satisfied if you replace D by D plus A. And so any two connections always differ by such an endomorphism, and conversely, the set of endomorphisms gives you all possible connections. So in particular, if you look locally, a bundle is trivial locally, and so it has the connection just given by the exterior derivative. That's well defined in the trivial bundle case. And so that means that locally, any connection is the trivial connection, the exterior derivative, plus some matrix of one forms acting on the section. And that matrix of one forms is called the connection one form. In particular, locally, if E1 through ER is a frame, then if a typical section will be, say, sigma I, sigma alpha, E alpha, these sigma alpha are functions, then you can define this connection, the trivial connection, D sigma will be D sigma alpha, E alpha. This is only defined where you have a frame. Okay? And so then any other connection, so D of sigma will be D sigma alpha E alpha plus sigma alpha D of E alpha. Okay? And so this is now some one form with values in E, according to our definition of a connection. So we can write this as A alpha beta E beta. So you can write this whole thing as D sigma alpha plus A plus sigma beta A beta alpha E alpha, yeah, tensor E alpha. And so this quantity here is called the connection one form. So it's a matrix of one form. Okay, that's the local description. So there's a feature of connections which is kind of respects the category in which you're working. So for example, in this situation, we're working with vector bundles, which are really just families of vector spaces. And so any operation that we can do to a vector space, we would like to be able to see it reflected in an operation on the connections. So for example, if you've got a connection for a vector bundle, you would like to know, is there a dual connection for the dual vector bundle? Or if you've got two vector bundles and you take their tensor product, is there a natural connection that you get for the tensor product from the two connections for these vector bundles? And the answer is yes. So this connections let's just say it loosely, they respect multilinearity. And if you work with these things enough, you start to see that in some sense connections give you the sort of infinitesimal version of a vector bundle. So it's like linearizing the vector bundle somehow. This is the derivative that you get for that vector bundle. So there's the dual connection. So let's say D check for E star when D is given for E. And it's defined as follows. So if you've got a section, sigma is a section of E, and maybe alpha is a section of the dual, then you can pair these two things, and you get a function on the manifold. And that function you can differentiate with the exterior derivative. So the rule is, by definition, that what you should get here is the dual connection alpha on sigma plus alpha d of sigma. Now you have to understand this in the correct way. So this is a differential one form. So is this. But it's this quantity that you plug the one form into, when the vector into, sorry, and then that gives you an element of the dual vector bundle, and then you pair that with this. And similarly here, this is a one form with values in the vector bundle, so if you plug in a vector, you get something in the vector bundle, and you can pair it with something in the dual. So I'm going to write this a lot. You have to understand this in this way. A common notation is that if you take a tangent vector, C, you will often see this written in this way. That's the way to express that you're feeding in the vectors. Okay? So that's a dual connection. Then you have product connections. So if you've got, say, E1 and E2 with connections D1 and D2, then you can make any product of E1 and E2. So I'll write it as a general product, but it could be the tensor product, could be the wedge product, and so on. So what's the connection? What's the connection, the product connection for these things? So let me write it as D, and loosely speaking, D1 times D2, that's the connection product. So I'm supposed to tell you what D does to a pair, say sigma 1 times sigma 2. So that's the product of two sections. And this should be D1 sigma 1 product sigma 2 plus sigma 1 product D2 sigma 2. That's the definition of the product connection. And one interesting special case is, so by induction, you could look at the determinant of a vector bundle. So if this E has rank R, this is just the rth wedge product of E. That's what the determinant bundle means. And so if you've got a connection D for E, and you take, say, sigma 1 up to sigma R sections of E, then take their wedge product, you get sigma 1 wedge, sigma R, and so D of the determinant of E connection, what's that going to equal? That's going to be the sum, sigma 1 wedge, so D sigma I, sigma R. I going from 1 to R. So this is, of course, if these sections are not independent, then this quantity is going to be 0. So the only time you get something non-zero is if they are independent. And then when you apply this D to sigma I, the only part you're going to preserve here is whatever is a multiple of sigma I. So if you do this, for example, if these sigma 1 through sigma R form a frame, then what you'll see is that the connection for the determinant bundle is actually the trace of the connection. So let me say it like this. D of det E is equal to the trace of E, of D, sorry, D sub E. So you should go through in the notes and see exactly what this all means. But, I mean, if you're interested, but this is another instance of what I said before, that the connections, they kind of capture the vector bundles infinitesimally. So the infinitesimal version of the determinant is the trace, right? That's the derivative of the determinant is the trace. And so you see that phenomenon here in particular. But we're going to use this actually. It's everything I'm trying to use later. Okay, so I mean, this is all well and good, except that what we've seen so far is that there are tons and tons of connections for any given vector bundle. Infinitely many connections, as many as there are sections of this vector bundle. So any smooth section of this vector bundle will give you a connection. So it's some huge infinite dimensional space. And that's a problem because, well, I mean, what kind of geometric information would you expect to get from such a huge family of objects? In fact, all you can really extract from it meaningfully is topological information. So you can define things like Chern classes of vector bundles. This is something I don't want to wade into in this lecture, but I'm happy to talk to anybody interested in that afterwards. But the next goal is to try to, when we have additional geometric hypotheses, to try to find subsets, special subsets of these set of all connections. And somehow the more natural a geometry is, the easier it should be for you to identify some canonical subset of connections. And if you're really, really lucky, that canonical subset will be a singleton. And so then you have the geometry is represented in the theory of differentiation for that particular vector bundle. And then you can maybe extract particular information about the geometric object by doing calculus. So that is certainly what we're going to do ultimately. So right now I'm going to just identify one type of special connection, and then I'll stop and we'll pick it up next time. But okay, so if the vector bundle E to M is endowed with a Hermitian metric, and you say the connection D is compatible with, let's give this metric a name, H, if, so you look at H of acting on two sections, sigma 1 and sigma 2. This is now a function. So you want to say, what's the derivative of this function? And this will be analogous to this story here, except that these are now sections of the same bundle. And so that's going to be our requirement. So this will be H of D sigma 1, sigma 2, plus H of sigma 1, D sigma 2. So remember before I said that a metric H can be thought of as a section of the dual tensor with the complex conjugate of the dual. So if you like, when you have this metric H and these two sections, this is a pairing of H with sigma 1 tensor sigma 2. So there's actually three objects here. So in general, the full expression should be, there should be a third term here, which is the induced connection on these bundles, E star tensor E star conjugate, H on sigma 1, sigma 2. And the requirement is that this thing is 0. So that's another way of saying the same thing. This exactly means this. Okay, so if you now have two such connections, say D tilde is another, then you can take the difference of the two. Well, you see this term here doesn't depend on the connection. So you get 0 is h of d minus d tilde sigma 1 sigma 2 plus h of sigma 1 d minus d tilde sigma 2. So this is our endomorphism, one form valued endomorphism, and it's skew Hermitian. So in other words, if you've got a skew Hermitian endomorphism and a Hermitian connection, then you get a new Hermitian connection just by adding the endomorphism to it. So these are not unique. There's still many, many of these. So what we're going to do next time is look at two special cases in which we can further impose geometric hypotheses and guarantee that this endomorphism is uniquely determined. Okay? So that will be the Levi-Civita connection and the Chern connection. We'll talk about those next time.